So let's get started. We are going to continue our discussion regarding the kinetics of a particle. Last time we learned how to draw the free body diagram for a particle that is moving, and we have forces acting on that particle. And we learned that we have two diagrams. We have the free body diagram and we have the kinetic diagram. So today we are going to learn how to use the equations of the motion, especially in the rectangular coordinates, which mean that the movement is going to be in X or in Y or in Z. Assume that we have a box or crater, and we have a man here. He is pushing that box with a certain angle, and we need to know how large a force F must be exerted to start moving the crate or the box. And also we need to know what factors influence how large this force must be to start moving the crater. So also we need to know if the crater starts moving, is the acceleration presented here? And also, what would you have to know before you could find these answers? So in order to have answers for all of this, we need to understand how to use the equation of motion. You may answer some questions, depends on statics, but in order to answer all questions, we need today to use the equation of equilibrium, so that we will be able to know all the answers. So the equation of motion, which is the forces acting on a particle, unbalanced forces, is going to create acceleration acting on the particle. So the vector force should equal the mass times the acceleration vector. So when dealing with problem like that, this equation is best to use when the problem requires finding forces, especially forces perpendicular to the path of the particle, also to find the accelerations, velocities, or the mass. And you need to remember this: unbalanced forces cause acceleration. If the summation of the forces on the particle is in equilibrium, that means the acceleration is zero, like we learned from statics. This equation, we can generate three scalar equations from the vector equations. So here we have vector equation. We can write three scalar equation depends on this one. If you do remember, since this one is scalar or vector equation, that means I can say that the summation of the forces in x, I, plus the summation of the forces in y, j, plus the summation of the forces in zk is going to equal the mass times axi plus ayj plus azk. Like we said that the acceleration is a vector quantity, so you are going to have component into x and into y and into z. Since I should equal I, the component of I should equal I can say that the summation of the forces in x equals the mass times the acceleration in x. Also, I can say that the summation of the forces in y should equal may, and the summation of the forces in z direction equals maz. So I can use the vector equation to write three scalar equations. And in order to use the equation of equilibrium in rectangular coordinates, we are going to use the scalar equations. So how I'm going to solve the problem? The procedure is simple. First, we need to develop free body diagram. It's very important to do that. And in the previous lecture, we'll learn how to draw the free body diagram. We are going to establish your coordinate system. You need to choose convenient coordinate system. And we are going to draw the particles free body diagram. We are going to show all the external forces. And then these external forces usually are going to include the weight of the particle, the normal forces acting on the contact surface, the frictional forces also acting on the contact surface. Make sure that in the question whether the surface contact is smooth or not. And also we are going to have applied forces. So those are the expected forces when you are going to draw the free body diagram. Also, we need to show the inertial forces, the MA vector. Sometimes we call this the inertial force on a separate kinetic diagram. So we are going to have free body diagram for the external forces, and for the MA, we are going to have kinetic diagram. We learned how to do that in the previous lecture. Also, you need to make sure that any friction forces act opposite to the direction of the motion. So take care of the direction of the frictional forces. If the particle is connected to elastic linear spring, then the spring force equal Ks. Also, you should include that in the free body diagram. So if you have a spring connected to the particle, do not forget to include the spring force. If you are going to have a frictional force, make sure that the direction is opposite to the direction of the motion. Then you are going to be able to use the equations of the equilibrium. So if the forces can be resolved directly from the free body diagram, like the 2D problems, we are going to use the scalar form of the equation of the equilibrium. So when I draw the free body diagram, then if I can resolve all the forces into X and into Y, then I'm going to use the scalar form of the equation of motion. If the case is complex, like the 3D, we are going to make vector analysis. Here we have the Cartesian vector formulation for the equation of motion, or the Newton's second law, like that. And we can write it like that. And we said that from these equations, we can generate 3 scalar equations. Usually, when you are going to deal with 2D, we are going to use the scalar equations. We are going to use the equation in X and the equation in Y. Also, sometimes we need to determine the velocity, or sometimes we need to determine the position of the particle. Like you can see in the equation of the motion, we have relation between the forces and the acceleration. But if we were asked about the velocity or the position of the particles, in that case, we need to use the kinematics equations. Remember this kinematics equation, we need to use that. And if you are going to deal with constant velocity or constant acceleration, in that case, I can use those one instead of those one here. And we have lecture about that, how to use those equations. So we know that the second law only provides solution for the forces and the acceleration. Forces and acceleration. If the velocity or the position have to be found, then we need to use the kinematics equations in order to determine the velocity or the position. Make sure that you have consistent positive coordinates. Remember the positive coordinates, direction, when you are going to use the equation of the equilibrium. So now let's solve example so that we are going to develop skills in order to use the equation of the equilibrium for particles that on the move. So here we have crate with 50 kilograms. Here we have a box with 50 kilograms in the figure below. Rests on horizontal surface for which the coefficient of kinetic friction is equal 0.3. That means that the surface here is rough. And also, you are going to say that the box is going to move. So if the box is going to move, the friction here is 0.3. Remember, this one is not static friction. This one is kinetic friction. The crater is going to subject it to 400 newtons, like you can see here, with an angle. That force is going to be connected like that. We need to know the velocity of the crate of that box in 3 seconds starting from rest. So we need to know the velocity of the box after 3 seconds from applying that force. And remember that the crater is going to move from the rest. It's going to move from the rest. That means the initial force for that crate is 0. So what should be done in order to solve this problem here? We are going to use the equations of motion because we need to relate the acceleration of the box and the forces that cause the motion. So the best way to solve this problem is to use the equation of the equilibrium. So first, to use the equation of motion, we need to draw the free body diagram. And we said that in order to draw the free body diagram, that includes 3 steps. Step number 1, define an inertial coordinate system. And in that case, it's going to be fixed to the ground because the motion is going to be this way. So I need to put the coordinate system that help me to solve my problem. So here, the x and y, I'm going to put x here and y there. Okay, of course, the acceleration, I'm going to expect that the acceleration is going to be in this direction, the direction of the motion. Then I need to draw the blocks free body diagram showing all the external forces. Remember, we said that the free body diagram includes the weight of the particle, the normal forces, the frictional forces. Also, if we are going to have springs, we need to put it here, and the applied forces. Here we don't have any spring, and we have the weight of the box is going to act down, and we have the normal force is going to be perpendicular to that surface, and we are going to have frictional forces, and we have the applied load. So we have the applied force here. We have the frictional forces, mu k and c, and here we have the normal force, and here we have the weight of the box. So I know the mass is given, I know the gravity, mu k is given, nc, I need to know the value of nc so that I can substitute it here. Then I need to draw the blocks kinetics diagram. So here we have the value of mass and the value of gravity. Then I know the weight of the box. Here the mu k is 0.3. I don't know the value of nc. So also I don't know the value of nc here. And here we have the kinetic diagram. As a result, I'm going to have acceleration in the direction of the motion. And I can say that the acceleration here is in direction of x. So I'm going to call it ax. What about y? Do I have acceleration in y? In y direction, I don't have any movement. That means the value of ay is going to be 0. So now I come up with the free body diagram showing all the external forces. And here we have the kinetic diagram showing the inertial force. So now I'm in position to use the equations of motion. And since we are dealing with 2D problem, then I'm going to use the scalar form of the equation of motion. So in this case, we're going to apply the equation of motion in their scalar component form. And also, if I have any force here, inclined force, I need to decompose it into x and into y. So I'm going to use this equation and that equation here. And also, I need to take care of the sign convention. So in this equation, the summation of the forces in x direction should equal max. And the other one, the summation of the forces in y-axis should equal may. Like I said, since I don't have any movement in y, that means the ay is going to be 0. So the particle is in equilibrium in the y-axis, but I have movement in x-axis. So this force needs to decompose into x and into y. In x, it's going to be 400 cosine 30, and in y, 400 sine 30. Now I can use those equations. So I'm going to start with the summation of the force in y-axis. We say that since we don't have any movement in y, that part is going to be 0. Then I'm going to have this value, and that value, and that value. This value is going to be negative, this one is going to be positive, and this one is going to be positive as well. So I have positive NC, negative 490.5, and here I have positive 400 sine 30. I have one unknown, which is NC. I can easily solve for NC. NC came out to be 290.5 newtons. Then I'm going to use this equation here. The summation of the forces in x should equal the mass times the acceleration in x. In x, I have only the frictional forces, 0.3 NC. Now I know the value of NC, so I'm going to substitute it here. I have also the 400 cosine 30. This one is positive, this one is negative. And here I have the inertial force here, which is positive, or in that equation, the forces here should equal the forces there. And this one should be positive 50. We assume the direction is there. If the answer came out to be negative, that means the acceleration is slowing down, not speeding up. Then here I have only one unknown, which is the acceleration. We solve for the acceleration, and the answer came out to be 5.185 meter per second squared. So now we got the value of the acceleration. And the value of acceleration here, like you can see, it's constant. It's not going to change. It does not depend on the time. That means the acceleration is constant. Sometimes the acceleration depends on the time. But here, since the value is constant, that means along the way, the value of the acceleration is going to be constant, and it's going to be speeding up. Now, in the question, if we get back to the question here, it's required to determine the velocity of the crate in 3 seconds starting from the rest. So here I just get the value of the acceleration, but they want the value of the velocity. So what should I do in this case? So I need to use the kinematics equation in that case, because I need to know the value of the velocity. And here I have only the value of the acceleration. So now I'm going to solve a kinematic equation. I have a particle, and that particle starts from rest. That means the initial velocity is 0. Then we need to know the value of the velocity after 3 seconds. So the acceleration is constant here because the applied force is constant, and also here we don't have any variable inside the equation of the acceleration, and the initial velocity is 0 because he said that the box starting from the rest. So now, because the acceleration is constant, I have three options using this equation or that equation here. So which one should I use? It didn't ask about the position. And I don't have any information regarding the position. I have the time, I know the constant acceleration, I know the initial velocity. So this equation is the best one need to be used. So I'm going to use this one. I need to know the value of the velocity. I know the initial velocity. I know the value of the acceleration, and I know the time. The time is 3 seconds, and the acceleration is here, and the initial velocity is 0. So I can use this formula here, and I can easily determine the value of the velocity. The value of the velocity after 3 seconds came out to be 15.6 meter per second. So after 3 seconds, starting from the rest, the box is going to move with a velocity equal 15.6 meter per seconds. So we finished from that example. If you have any questions regarding this example, please. Example 2. In example 2, we have a motor here is going to wind a cable. So it's going to drag that cable here. As a result, that box is going to move. And they are going to drag that box with constant acceleration. So the acceleration is going to be constant. And the weight of the box here is 20 kilogram. And that one is going to move a distance. So here we are going to move a distance equal 6 meters in 3 seconds. So after I operate that motor here, the box is going to move 6 meters in 3 seconds. And starting from the rest, that means the initial velocity is 0. And they give us the coefficient of friction, UK equal 0.3. That means that surface is a rough surface. So we need to know the tension developed in the cable. We need to know the tension developed in the cable. So we need the value of T here in that cable. So like I said, that first we need to draw the free body diagram and kinetic diagram, and then we are going to be in a position to use the kinematics equation, because here I don't know the value of the acceleration. If I know the value of the acceleration, I can directly use the equation of motion. But since I don't know the acceleration of that crate, then I need to use the kinematic equation to get the acceleration. Then I'm going to be able to use the equation of the motion to determine the cable tension. So let's see the first step, the free body diagram. We need to define an inertial coordinate system. So this time, since the surface, here we have angle equal 30, then we are going to put the coordinate system aligned to that surface here. It should be aligned to that surface. So I'm going to have X and Y, because in X we are going to have the direction of the motion. So in this problem, we need to define an inertial coordinate system. It's going to be aligned to the surface, which means that it's going to make 90 degrees with the x-axis, the horizontal axis here. So since the motion is up the incline, we are going to rotate xy axis so that the x-axis align with the incline. Then the motion is going to occur along the x-axis. Then I need to draw the block's free body diagram showing all the external forces. So I need to show all the external forces. We have the weight of the box acting down. We have the tension in the cable here. And also we have the value of the N, the normal force. And we have frictional force. should be opposite to the direction of the motion. So are going to have the weight which is acting down, we have the tension in the cable, we have the frictional forces opposite to the direction of the motion, and we have the normal force. And also we need to draw the kinetic diagram. So we are going to have MA in the direction of the motion. We have MA, M in that case is 20. So I'm going to have 20A. We are going to call this AX. And here also you could put AY, but in this case AY is 0. So now we have the free body diagram, and we have the kinetic diagram. Now in order to determine the value of T, I need to know the value of A. So in this example, we don't know the value of A. We don't know the value of the acceleration. So we need to use the kinematics equations first in order to determine the acceleration. So here we know that the position is going to be 6 meters after 3 seconds. So after 3 seconds of motion, the position of the box is going to be at 6 meters. And the box is starting from the rest. That means the initial velocity is going to be 0. And in this case, he said that the acceleration is constant. So I'm going to use one of these equations here, either the first, second, or the third. So it depends on my givens here. I need to choose appropriate one. So here, if let's say that I'm going to use this equation here. So in this equation, I know the value of S. I know the value of S naught because S naught is going to be 0. I know the initial velocity. I know the value of T. We said that the position is going to be 6 meters when the time is 3. Also, I know the time. The only unknown is AC. So if I'm going to use this equation, I'm going to be able to determine AC. So if I'm going to use this equation, what will happen? The velocity when the time is 3, I don't know. I know the value of Vt, the initial velocity, which is 0. I know the time. So here I have V, I don't know, and I don't know the value of AC. So I'm not going to use this equation. Similarly, in this equation, I'm going to have two unknowns, the value of V and the value of C. So here is the only equation that is going to help me to determine the value of AC. So I'm going to use this formula here. The value of S equals 6 meters. Vt is 0. Here, the value of S naught also is 0. And the value of T is 3. And I have only one unknown, which is AC. AC came out to be 1.33 meter per second squared. So now we know the value of the acceleration. So now we know the value of A. Now we are in position to use the equation of motion. So also we are going to apply the scalar equations, the equation in X and the equation in Y. We are going to use this one and that one. And here is the direction of X, and here is the direction of the Y. So now we are going to start with the summation of the forces in Y-axis. So now Y-axis is here. Y-axis is here, and X-axis is there. We need to decompose the weight into X and into Y. Since this angle here is 30, that means the angle here also is going to be 30. So in this axis Y, the component of the weight is going to be down and is going to be 20 cosine 30. And in Y here, I have the normal force. So in Y, I'm going to have minus 20 G cosine 30 plus N equal 0. G, we are going to use 9.81. The value of N came out to be 160 9.9 newtons. So now I know the value of N. And of course here, the value of AY is going to be 0 because I don't have any motion in Y axis. Then I'm going to use that equation here, summation of the forces in x-axis. Now x-axis is there. We are going to have the value of T, and also we are going to have the friction. The T is going to be positive, the friction is going to be negative, and also I have a component for the weight, and it's going to be negative. We are going to decompose here and there. We are going to have a component for the weight. It's going to be 20g sine 30. So in x, I'm going to have T is positive, and I'm going to have component for the weight, which is negative, and I'm going to have the friction, which is negative as well. Now I know the value of N. I'm going to substitute the value of N here. And regarding the other part, the kinetic part, I'm going to have 20A. Now I know the value of A from here, so I'm going to substitute the value of A here. Now the only unknown is the T. So easily I can solve for the T. So the value of the tension came out to be 176 newtons. So now I solve the problem. I determine the tension in the cable. So the tension in the cable came out to be 176 newtons. Do you have any questions regarding